Noise, vibration, harshness. All three are readily identifiable, but troubleshooting noise, vibration, and harshness can be difficult. Hello, and welcome to MasterTech. Today we're going to cover important information that should improve your ability to solve noise, vibration, and harshness problems. First, we'll discuss noise, vibration, and harshness basics. We'll apply steps 1 through 4 of the standard troubleshooting procedure to isolate noise, vibration, and harshness problems. And we'll finish by using all 6 steps of the troubleshooting procedure to solve a common NVH condition. When sound or noise is heard, there is always an object that is vibrating, and in turn, air that is being made to vibrate. Vibration is the repetitive motion of an object, either back and forth, up and down, or side to side. In cars and trucks, vibrations are caused by rotating components, such as wheels and tires or cylinder firing impulses created by the combustion process in the engine. Both sounds and vibrations are measured in cycles. In the case of a ruler vibrating, a cycle represents the complete path of travel, beginning at the midpoint, through the lowest extreme, through the upper extreme, and back to the midpoint where the cycle begins again. The number of times an object completes its cycle during a given time period is called its frequency. Frequency is measured in cycles completed per second, and the term for cycles per second is hertz, abbreviated Hz. Amplitude refers to a vibration's intensity. Seen here, amplitude is the total distance between the top and bottom of the wave. As the amplitude increases, so does the intensity or volume, as long as it can be heard by the human ear. Humans can hear sound which falls within these sound intensity and frequency ranges. Because the human ear is sensitive to only a limited range of frequency and sound intensity, not all vibration is heard as sound. Generally, the human hearing range is 20 to 20,000 hertz. For example, an object vibrating at a frequency of 10 hertz, like a steering wheel when there's a tire imbalance, does cause sound. Because the sound's frequency does not fall within a human's audible range, it goes unheard. On the other hand, an object vibrating at a frequency of 50 hertz is within a human's audible range, but is still hard to hear. Its sound is similar to a low-speed droning noise. An object vibrating at a frequency of 100 hertz creates a sound similar to a mid-speed droning noise. And an object vibrating at a frequency of 200 hertz creates a sound similar to a high-speed droning noise. Order refers to the number of disturbances created in one revolution of a component. For example, one high spot on a balanced wheel creates 1 disturbance per revolution. If the wheel rotates 10 times per second, the first order vibration is 10 hertz. Let's add another high spot, producing an additional disturbance per revolution. If the wheel is rotating 10 times per second, it now produces 2 vibrations per revolution, creating a second-order vibration of 20 hertz. Harshness can be considered a vibration that occurs as a shock when tires pass over road surface variations or road joints. Refer to this month's reference book to familiarize yourself with other important concepts like beat and resonance. Knowing the symptom's frequency is often vital when isolating trouble spots. Let's test our abilities. Does this sound have a frequency of A, 50, B, 100, or C, 200 hertz? If you said C, 200 hertz, you are correct. Your ability to recognize vibrational frequency levels is important when determining which components are causing excessive noise and vibration. We'll demonstrate this later on during step 4 of the troubleshooting process. To demonstrate how to troubleshoot the vast range of NVH problems, let's go through each phase of the troubleshooting process in detail. I'm sure you're familiar with the 6-step troubleshooting procedure. verify the customer complaint, determine related symptoms, analyze the symptoms, isolate the trouble, repair the trouble, and verify proper operation. The first step is to confirm and reproduce the condition as described by the customer. Because of the complexities of NVH problems, you should try to speak directly with the customer to avoid any miscommunication. It's best to have the customer with you in the vehicle when the problem occurs. Once you and the customer verify the complaint, you can then determine related symptoms. Determining related symptoms involves gathering as much information as possible and associating the noise, vibration, or harshness with a specific vehicle component group. When gathering information, use a worksheet like this one found in your reference book to record important information like make and model, year, engine size, etc. When the symptom occurs, note the corresponding speed, RPM, and gear. Record a detailed description of the symptom or symptoms and identify the frequency range of the noise or vibration. Identifying the symptom frequency helps to isolate the trouble to specific component groups. For best results, use an electronic vibration analyzer to record vibrational frequency. The electronic vibration analyzer is available through professional service equipment. Refer to the reference book included with the EVA for operating instructions. If you don't have an electronic vibration analyzer, you will have to rely on your senses to record noise and vibration frequencies. The second part of determining related symptoms is associating the noise, vibration, or harshness condition with a specific vehicle component group. Determining whether the noise or vibration is associated with engine speed components or vehicle speed components is the first and most important association. Once this is determined, the number of suspect components is greatly reduced. The following tests help to determine if the trouble is related to vehicle speed or engine speed, and ultimately help you pinpoint the exact location of the NVH trouble. A tire inspection should be performed for all noise, vibration, and harshness complaints unless the disturbance only occurs when the vehicle is at a standstill. Check inflation pressure and look for unusual wear, especially cupping, flat spots, feathering, and shoulder wear. These conditions can cause tire growl, howl, slapping noises, and vibrations throughout the vehicle. You'll need to record engine RPM during the road test, so use a scan tool if the vehicle does not have a tachometer, and install an electronic vibration analyzer if one is available to record the frequency of problem vibrations. When test driving, slowly accelerate up to highway speed and look for disturbances that match the customer's description. Note the vehicle speed and the engine speed or RPM when the disturbance occurs. If the disturbance is a vibration, use an electronic vibration analyzer to record the frequency of the disturbance. If an analyzer is not available, use your senses to estimate the frequency. With the vehicle stopped, record this information on your data sheet. Once you have noted engine speed, vehicle speed, and the frequency of the noise or vibration, accelerate to a speed slightly higher than the speed at which the problem occurs. Shift the vehicle into neutral and coast down through the vibration range and note if the noise or vibration is present. If the noise or vibration still occurs in neutral, it is definitely vehicle speed sensitive. And at this point, the engine and torque converter can be eliminated as potential NVH causes. If the noise or vibration does not occur during the neutral coast down test, decelerate and safely downshift to the next lower gear. Then operate the vehicle at the previous engine RPM. If the problem returns, the noise or vibration is engine speed sensitive, and the engine or torque converter are the most probable locations of the problem. You may repeat this test in still lower gears and in neutral to confirm your results. The first steering input test is intended to determine how much wheel bearings and other suspension components contribute to an existing vehicle speed-related noise or vibration, especially those relating to noises like howl or growl, grinding, and roaring. With the vehicle at the vibration speed, drive through sweeping turns, first in one direction, then in the other. If the existing noise gets worse or goes away, worn wheel bearings, worn hubs, and abnormal or excessive tire tread wear are all possible causes. The second steering input test is used to isolate problems that occur only when turning. Perform the previous procedure, only this time coasting with the car in neutral. If noise or vibration are generated, the problem is independent of engine speed. Check for worn wheel bearings and worn suspension bushings. If noise or vibration are not generated while coasting with the car in neutral, engage the transaxle and alternately accelerate and decelerate while making sweeping turns. If noise or vibration now occur, the problem is dependent upon engine load. Check for damaged CV boots, worn CV joints, and look for loose or missing lug nuts. If you hear a clunking sound when you quickly accelerate or decelerate, check for worn engine and transaxle mounts and inspect the suspension bushings. The next three tests, the neutral run-up test, the brake load test, and the engine accessory test, are performed when you get back to the shop. The neutral run-up test is designed to identify engine speed-related vibrations. Use it as a follow-up to the downshift test or when the customer complains of vibration at idle. With the vehicle in neutral or park, slowly increase the engine RPM looking for disturbances that match the customer complaint. If noise or vibration occur, you have identified an engine speed-related problem. Note at what RPM the vibration occurs and obtain a frequency reading if possible. The brake load test is designed to identify engine speed-related noise or vibrations that were not reproduced by the neutral run-up test or the neutral coast down test. It also works for noise and vibrations that are sensitive to engine load or torque. Block the front and back wheels. Apply both the parking brake and the service brake. Then place the vehicle in drive. Increase the engine RPM looking for vibrations that match the customer's description. Never perform the brake load test for more than 5 seconds or damage to the transaxle may result. Repeat the procedure with the transaxle in reverse. If noise or vibrations occur, worn engine and transaxle mounts are probable causes. If you have determined that the noise or vibration is definitely engine speed related, perform the engine accessories test to narrow down the possible trouble source. Remove the accessory drive belts and increase engine speed to the RPM at which the noise or vibration occurs. If the problem persists, you can eliminate the belts and accessories from consideration. If the problem goes away, the trouble source is either a belt or an accessory problem. Gathering information and thoroughly testing will allow you to determine related symptoms. You should be able to determine if the noise, vibration, or harshness is engine speed related or vehicle speed related. In most cases, you'll narrow the trouble source down even further. It's important that you clearly understand how to determine related symptoms. So before we go to the next step, let's test what we've learned with a review question. A clunking sound that occurs while alternately accelerating and decelerating is most often caused by problems in which of the following components? A, wheel bearings and CV joints. B, brake pads and rotors. Or C, engine and transaxle mounts and suspension bushings. The correct answer is C. If a clunking sound occurs while alternately accelerating and decelerating, you should inspect the engine and transaxle mounts and also inspect the suspension bushings. There are 2 steps involved when analyzing symptoms. The first step is to determine whether or not the customer's claim is actually an abnormal condition. This is very important because once an attempt has been made to repair what may be a normal condition, the customer may become convinced that he or she has a true concern. The second step is to classify the noise, vibration, or harshness symptom. Each noise, vibration, and harshness classification leads to common causes that help you isolate the trouble. Depending on the symptoms specific to the vehicle you're working on and the extent of testing performed, you should be able to place the noise, vibration, or harshness into one of these classifications. Each classification has a unique set of probable causes allowing you to isolate the trouble. We will briefly cover shake, beat, and droning. Refer to your reference book for descriptions of the other classifications and their common causes. Shake is a common vibration and is identified by severe vertical or lateral vibration of the body, seats, or steering wheel. Shake generally has a low frequency between 10 to 30 hertz and occurs at speeds between 25 and 45 miles per hour. It also can occur at specific highway speeds. Shake symptoms are most often caused by wheel, tire, and brake area problems. Actually, wheel, tire, and brake area problems cause a major portion of noise, vibration, and harshness, so the following checks apply to other symptoms as well. It's a good idea to identify whether the shake symptom vibrations are felt in the steering wheel or if they are felt in the seats and floor. If the vibration is felt in the steering wheel, the problem is most likely related to the front wheel assemblies. Vibrations felt in the floor or seat are most likely related to the rear wheel assemblies. This may not always hold true, but use it as a general rule when isolating problems to the front or rear. The first check is wheel and tire installation. Check that all the lug nuts are torqued equally and properly. Look for non-uniform mating surfaces, especially when dealing with aftermarket wheels. Differences in lug nut torque and non-uniform mating surfaces are also major causes of shimmy and brake shudder. And inspect the tire, making sure the bead is uniform. You will want to check for excessive lateral and radial runout on both the tire and the wheel. Excessive wheel hub runout is also a potential cause. And finally, check for tire imbalance. If all of the previous checks, installation, runout, and balance, are within specs, you could have excessive force variation in the tires. Force variation refers to differences in the stiffness of a tire's sidewall and tread as it rotates and contacts the road. Because force variation is only measurable when the tire is under load, it's very hard to detect. When force variation is suspected, substitute a known good assembly and see if the problem persists. We will cover wheel, tire, and brake area troubleshooting again in the sample problem. The symptoms and common causes of shake are outlined in your reference book. We have just demonstrated how effectively classifying your vehicle's symptoms enables you to isolate the trouble. Just check the common causes relative to the classification. Beat is one of the most difficult noises to troubleshoot because it involves combinations of two or more different component frequencies causing a modulating sound like this. If beats occur only when idling, your possible causes are somewhat more limited than beats that occur when driving. A beat while idling can result from one or all of the following: differences in frequency between the engine and the accessories, between the engine and exhaust, between the accessories and the exhaust, and even between the engine and the engine's own firing impulses. The problem is compounded when driving because any one of the frequencies we just mentioned can combine with one or more vehicle speed-related frequencies, like wheel speed or half-shaft speed. Droning, another common noise, is equally challenging to troubleshoot because it can happen at any time. During low-speed to middle-speed driving, droning is a low-pitched noise that is non-directional. It seems to come from all over. It's hard to hear as a sound, but it feels as if your ears are being pressured. The frequency is generally 20 to 100 hertz. During high-speed driving, droning is more of a whirring noise that is non-directional and uncomfortable to the ears. In severe cases, the effect is still felt after leaving the car. The frequency is generally 100 to 200 hertz. The correction of beat and droning problems can take much time and effort. Therefore, it's best to make a complete overall inspection of the vehicle, checking to compare current conditions with what they should be. Use this inspection chart as a guide when performing the overall inspection. You will often find simple causes that would otherwise escape detection. The inspection chart can be found in your reference book. Because there are so many possible causes for both droning and beat, a little patience will go a long way when troubleshooting. Refer to your reference book for additional information regarding probable causes of droning and beat. You will also find a complete breakdown of generating conditions and probable causes for other symptoms like harshness, brake shudder, shimmy, etc. When analyzing symptoms, remember, your first step is to determine if the customer's claim is actually an abnormal condition. This is especially important with beat problems. Some beat problems are the result of vehicle design and cannot be corrected. After determining that the customer's claim is an abnormal condition, proceed to assign the problem NVH to a specific classification. As we've seen, effectively classifying a vehicle's NVH symptoms enables you to isolate the root cause of the trouble. Let's make sure we can effectively classify before we go any further. While traveling at low speed, you notice a low-pitched noise that seems non-directional. It's hard to hear as a sound, but feels as if your ears are being pressured. You would most likely classify this symptom as A, droning, B, shake, or C, beat. A, droning is the correct answer. Let's proceed. By placing the noise, vibration, and harshness symptoms into specific classifications, you can then check various components and isolate the trouble. Another and sometimes quicker way, especially with vibrations, is to isolate components by matching the vibration frequency to the component frequency. In front-wheel drive vehicles, there are two major rotating component groups, engine and the driveline wheel assemblies. Each rotates at a different speed due to transaxle and differential gear ratios. You can pinpoint the component group responsible for a measured vibration by determining the rotational speed of each group. Problem vibrations that match the first, second, or third order frequencies of the major component groups indicate that the cause is most likely located within these groups. If the problem is vehicle speed sensitive, calculate the tire wheel speed. Follow the flow chart on your data sheet for easy calculation. There is an area on your data sheet for propeller shaft speed calculation. Propeller shaft calculation only applies to vehicle speed-related vibrations on rear-wheel and four-wheel drive vehicles. This will be covered in the April MasterTech release number 6. To calculate wheel speed, first find the vehicle speed at which the symptom occurs. Then divide that number by 5. Your resulting number indicates the number of 5-mile-per-hour increments. Multiply this number by the corresponding tire size frequency at 5 miles per hour. Refer to the tire revolution chart located in your reference book. The resulting number is the first-order tire wheel speed frequency. The second-order frequency is twice this number, and the third-order frequency is 3 times this number. If the symptom's vibration matches the first, second, or third-order vibration, it is most likely the result of problems in the tire wheel area. First-order tire wheel vibrations are usually the result of one of two conditions, excessive runout or excessive imbalance. These conditions must be eliminated step by step in order to attain a set of wheels and tires free from vibration-causing elements. Refer to your service manual for proper procedures. To determine engine-related frequencies, first determine the RPM at which the symptom occurs. Divide the RPM by 60, the number of seconds per minute, to determine the engine's first-order vibration frequency in hertz. For example, if the symptom occurs at 1800 RPM, the first-order frequency of the engine is 30 hertz. Likewise, the second-order frequency is 60 hertz, and the third-order frequency is 90 hertz. Therefore, if the problem vibration's frequency is 30, 60, or 90 hertz, it is most likely an engine-related vibration. You can take this another step and isolate accessory components. Belt-driven engine accessories often produce vibrations at frequencies that differ from the engine's frequency. Why? Because the drive ratios created by the different size pulleys cause the accessories to rotate at different speeds. The accessory frequencies are determined by calculating the size ratio between the accessory pulley and the crankshaft pulley. The crankshaft pulley will rotate at engine speed. For example, if the crankshaft pulley diameter equals 4 inches and an accessory pulley has a diameter of 2 inches, one crankshaft rotation equals 2 accessory rotations. At 1800 RPM, the accessory will be rotating at 3600 RPM. The frequency in cycles per second is 60 Hertz. Now, if the problem vibrations frequency is also 60 Hertz, the source of the problem is most likely the accessory. We have just covered the two most practical ways of isolating noise, vibration, and harshness problems. By classifying the problem symptom, then checking the most probable causes, and by matching the problem frequency to a component frequency. Once the trouble has been isolated, the last two steps, repairing the trouble and verifying proper operation, are fairly straightforward. Before we demonstrate all 6 steps in our sample problem, let's make sure we understand how to calculate component frequency with this review question. If a 4-inch crankshaft pulley is rotating at 3000 RPM, what is the frequency of the power steering pump if its pulley is 2 inches in diameter? A, 100 Hertz, B, 200 Hertz, or C, 300 Hertz? You're correct if you said A, 100 Hertz. Because of the 2-to-1 size ratio, the accessory pulley rotates at 6000 RPM when the crankshaft pulley rotates at 3000 RPM. To obtain a cycles per second frequency, you divide 6000 by 60. It's now time to apply what we've learned to a sample problem. The first when solving problems is to verify the customer complaint. In this case, the customer says her car starts to shake while driving at speeds between 40 and 50 miles per hour. To avoid miscommunication, we'll take the customer with us to verify the complaint. After filling out the vehicle information section of the data sheet, we'll check inflation pressure and inspect the tires for unusual wear. The tires look good, and there are no signs of cupping, flat spots, feathering, or shoulder wear. In this case, an electronic vibration analyzer is not available. We'll have to use our senses to estimate the frequency. We'll slowly accelerate, looking for disturbances that match the customer's complaint. The vehicle begins shaking at 45 miles per hour. At this speed, the engine RPM is 1800. The problem is a low-frequency vertical vibration of the body, instrument panel, and steering wheel. We estimate the frequency to be approximately 10 Hertz. After bringing the vehicle to a stop, we can record this information on the data sheet. The neutral coast down test should identify whether the trouble is engine speed or vehicle speed related. We'll accelerate to a speed slightly higher than the speed at which the problem occurs. Then shift the vehicle into neutral and coast down through the vibration range. The vibration still occurs, so we can conclude that the vibration is related to vehicle speed and can therefore eliminate the engine and torque converter as the source of the trouble. Just to be safe, however, we'll perform the neutral run-up test after we return to the service bay to further confirm our results. We have one more test to perform while driving. By taking sweeping turns at the vibration speed, we can determine if the wheel bearings and suspension components contribute to the vibration. The problem remains consistent throughout the turns. The wheel bearings and hubs are apparently not contributing to the vibration. After returning to the service bay, the neutral run-up test further confirms that the trouble is related to vehicle speed and not engine speed. Let's review our results so far. We have verified the customer complaint. We know the symptoms characteristics. We also know that the vibration is related to vehicle speed and the wheel bearings and suspension components are not contributing. Because the trouble is vehicle speed related, the only component frequency we will need to calculate is wheel speed. 45 miles per hour is the speed at which the vibration occurs. 45 divided by 5 equals 9. Multiply 9 by the corresponding tire size frequency at 5 miles per hour, in this case, 1.09 Hertz. The resulting wheel speed frequency at 45 miles per hour is 9.81 Hertz, which, when rounded off, is 10 Hertz. The trouble symptom is definitely an abnormal condition, so the customer's claim is justified. Classification is the next step. Let's look at the symptoms. The body, steering wheel, and instrument panel shake vertically at a low frequency of 10 Hertz at 45 miles per hour. We also concluded that the problem is vehicle speed related. These symptoms are best described by the shake classification. We determined that the claim was justified and have effectively classified the symptom. We can now isolate the trouble. Our trouble symptoms are classified as shake. Shake is mainly caused by abnormal conditions in the tire and wheel assembly. The shake frequency and the wheel speed frequency at 45 miles per hour are both 10 Hertz. This further confirms that the trouble lies in the wheel and tire assembly. We know that tire wheel vibrations are usually the result of one of two conditions: excessive runout or excessive imbalance. These conditions must be eliminated as possible causes. Because the runout of a tire wheel assembly directly affects the amount of imbalance, it should be corrected first. It's important to drive the vehicle before checking runout because flat spots may exist where the tires were resting on the ground. To get an indication of how much runout exists, we'll perform an on-car inspection. We'll first visually check the amount of runout from the front or rear by spinning each wheel by hand, looking for obvious signs of runout. In this case, the right front tire showed obvious signs of runout, so we'll measure that wheel first. In less obvious cases, it might be necessary to measure every wheel. Using a dial indicator, we'll measure radial and lateral runout. Before we measure radial runout, however, we'll tape the tread to ensure a smooth surface. We slowly rotate the assembly one complete revolution and zero the dial indicator on the low spot. Then, after rotating the assembly one more complete revolution, we note the total amount of runout indicated. In this case, radial runout is excessive. As a general rule, the maximum allowable assembly radial and lateral runout is 50 thousandths of an inch when measured off the vehicle and 60 thousandths of an inch when measured on the vehicle. For exact tolerances, refer to TSB 22-05-93. The lateral runout is within specifications. The next step is to remove the wheel assembly, mount it on a spin-type wheel balancer, and check radial and lateral runout again. The wheel assembly still shows excessive radial runout. We can therefore conclude that the runout is due to a problem within the wheel assembly. However, if the off-the-car runout was within tolerance, the excessive on-the-car runout would most likely result from wheel hub or axle flange runout, wheel stud runout, or from an improperly mounted wheel. Since the wheel assembly shows excessive radial runout, we need to determine if the runout exists in the tire, wheel, or a combination of both. To accomplish this, we'll use a procedure called match mounting. First, we'll mark the location of the high spot on the tire and the wheel. Then we'll place a mark on the tire sidewall at the location of the valve stem. This will be referred to as the 12 o'clock position. After breaking down the bead, we rotate the tire 180 degrees on the rim so the valve stem reference mark is now at 6 o'clock. In some instances, the bead will need to be lubed in order to rotate the tire on the wheel. We then reinflate the tire, making sure the bead is seated properly. After reinflation, we mount the assembly on the tire balancer and remeasure the runout. In this case, the runout is now within tolerance. The tire may be balanced and mounted on the vehicle. If the runout had not been within tolerance, we would have marked the location of the new high spot. In cases where the new high spot remains at or near the location of the original high spot, the wheel is the major contributor to the runout problem. It should be measured for excessive runout and replaced if that is the case. In cases where the new high spot is at or near a position 180 degrees from the original high spot, the tire is the major contributor and should be replaced. Always remeasure the tire wheel assembly runout after replacing the tire and make sure the runout is within tolerance before continuing. In the majority of cases, the first 180-degree turn of the tire will either correct the runout problem or indicate which component to replace. If the new high spot is in between the two extremes, then both the tire and wheel are contributing to the runout. Try rotating the tire an additional 90 degrees in both the clockwise and counterclockwise directions, measuring the runout after each rotation. Once runout has been brought within the tolerance, the assembly may be balanced. In our case, runout was within tolerance, so we balanced the wheel assembly, remounted it, and rechecked the runout. On the car, runout is within tolerance. We can now verify proper operation. To verify proper operation, we road test the vehicle again and look for trouble symptoms. No trouble symptoms occurred. We have effectively executed the 6-step troubleshooting procedure and corrected the trouble. Solving noise, vibration, and harshness problems can indeed be difficult. However, if you thoroughly perform each step of the troubleshooting procedure, applying the information provided in this month's MasterTech, you'll be able to solve even the toughest noise, vibration, and harshness problems. That's all for now. We'll see you next month.